Good morning. I'll be talking about my dissertation, which is on precision radial velocities in the near infrared. There are many collaborators to mention, but I specifically want to highlight my advisor, Larry Ramsey, Subrath Mahadevan at Penn State, collaborators from NIST, Wisconsin, and the team from Colorado as well, and many of the undergraduates and other students who have helped us with this vast project. Today I'll be talking about Pathfinder at PSU, some of our early experiments back in 2006 and 2007. I'll also discuss our exploration of near-infrared calibration systems, and then move on to Pathfinder at the HUT, where we did some on-sky tests. Finally, I'll finish up with my conclusions and discuss where we plan on going in the near future. You've heard much of the motivation this morning already. That is that MDORs provide a very excellent target for near-infrared surveys of planets, particularly because they have low mass and because the habitable zone is much closer to these stars. We can potentially identify habitable Earth mass planets around these stars more easily than we can around G-type stars. Unfortunately, the optical information available from these stellar spectra is much less than it is in the near-infrared, and so it would be very nice if we could move to the near-infrared to measure these stellar spectra. One of the major problems, of course, is telluric bands. In the H-band, here the telluric spectrum is shown in black and the OH lines are plotted in orange. In the H-band, there are many spectral features, some of which have actually been used, many telluric features, some of which have been used for precise radial velocities, in particular the CO2 bands, from which some of the most precise near-infrared radial velocities have been made, 6 to 10 meters per second. Now, the J-band similarly has many telluric features, and the Y-band is relatively clean compared to these other two spectral regions. Rayners et al. In 2010 did a study in which they measured the information content available in MDORs at a variety of resolutions, and including a variety of calibration sources, including the thorium-argon lamp and gas cells. There are no gas cells available in the near-infrared as of yet, except for the ammonia cell, but there is a lot of work being done in that region. But in general, what I'd like to highlight here is that the Y-band, again, offers a very nice opportunity for radial velocity precision measurements. And in particular, as you get to later stellar spectral types, you can find even more stellar information in the Y-band. This is for an M3, for an M6, and for an M9. And as you get to later spectral types, especially past M4 and M5, you can achieve higher precisions in the near-infrared potentially than you can in the optical. So the Pathfinder experiment was motivated to try and assess some of the challenges associated with making near-infrared precision radial velocity measurements. And in particular, we measured the Earth's rotation with respect to the solar spectrum. The amplitude of this signal is about 350 meters per second at State College, where the telescope, which was actually a fiber pointing at the sun, was set up. So if we can't measure this, then we might as well give up and go home. This is the setup at the HUT, but it's a very similar setup to what we had at Davy Labs. The light comes in through the fiber, bounces off a tiny mirror, which bounces off the collimating mirror, reflects onto the shell grating, which disperses onto the cross disperser, back onto the camera mirror, and then up into the Dewar, where we have a Hawaii 1K array. The fiber setup has a slit covering 300 micron fibers, one of which is a science fiber through which we get the stellar light or the solar light, and then calibration fibers adjacent to that. One of the major issues in the near-infrared is modal noise. Steve Osterman already went over some of this, but I'll show some of these slides here. This is laser light going through a fiber and imaged onto a white sheet of paper. You can see here some of the speckle pattern that we observe with this laser. And if this speckle pattern remained the same, it was constant all the time, we wouldn't really have a problem, but unfortunately the speckle pattern changes on the order of a few seconds. Here is an exposure taken just a few seconds later, and you can see the speckle pattern change quite a bit. The solution is to agitate or vibrate the fiber, which mixes the modes and produces a uniform illumination. It's not perfect, but generally it works pretty well. Here's extracted flat field spectra with and without agitation, and you can clearly see that when you do not agitate the fiber, you get a lot more structure in the flat field. Here's some of our early work at Penn State. You can see the solar spectrum which is shown here largely in white, some telluric features at the bottom, and thorium-argon light through an adjacent calibration fiber. You can also see one of the problems with our detector, which is multiplexer crosstalk, shown here as deep gouges in the array at the bottom in particular. This happens when bright light is from bright light in adjacent quadrants, reduces the counts in the other quadrants. Here's some of our extracted spectra. The green is telluric, the red is solar plus telluric, and the blue is thorium-argon. Again, emphasizing the relative lack of telluric features in the Y band, with the exception of here at the bottom, which is on the edge of the Y band. And here are some of our early results, where we achieved less than 10 meter per second precision in the Y band over short timescales. Some of the variations that you see in the first data set here is due to clouds passing between the telescope and the sun. Pathfinder is a warm spectrograph, and therefore we have to carefully select our filters when we're trying to minimize the thermal background. We started out with filters like those shown here on the left, the Spectragon 1300, the 1800, and the Bar 1300. As it turned out, the flaws beyond 2.5 microns, the transmission beyond 2.5 microns was actually detrimental to our system, and so we ordered some custom filters, two of which are shown here on the right-hand side, the Y-band Omega custom filter and a YJH custom filter. The filter scanning method isn't perfect. That deep gouge in the YJH shown here doesn't actually exist. And a PK50 filter as well. Ryan Tarian had a nice poster up the other day discussing an alternative PK50, which is no longer, since PK50 is no longer made. In the near-infrared, calibration sources are a little lacking, and this is a 25-second exposure of thorium-argon in the Y band. You can see some of the problems we have here. The argon lines are very, very bright, which induces multiplexer crosstalk and artifacts in our spectrograph, or on the detector rather. And there's many thorium lines, but there's a lot of them are eclipsed by these bright argon lines. We also did some experiments with uranium calibration source. This is a comparable uranium-argon exposure. There's more uranium lines than there are thorium lines, but there are also still these bright argon lines, and therefore we found that uranium-neon provided the optimal situation. That is that you have a lot of the uranium lines, but there are not as many bright neon lines as there are bright argon lines in the near-infrared. This is, again, a 25-second exposure. Our exposures in the Y band were more typical of 600 seconds, and in the H band, 300 seconds. A 600-second Y band exposure is shown here. Again, emphasizing that there's a lot of uranium lines to take advantage of, and very few bright neon lines. You can see some scattered light here from adjacent areas. During our frequency cone run, we created an atlas of the uranium neon spectrum over the H band, shown here. Each of the indices here are used to calculate the frequency of the given cone line. Some of the bright neon lines are highlighted with their wavelengths. And you can also see some of the thermal background, thermal continuum rather, in the uranium neon spectrum, since the hollow cathode is a thermal source, which does not appear, and the thermal source does not appear in the frequency cone because it is not a thermal source. We extracted these spectra and compared them to independently measured uranium lines from archived FTS data, and you can see they match up quite well. Blends become an issue if you're at lower resolution with uranium neon. There are just so many uranium lines that you have to be very careful about which lines you choose to use. This publication will be coming out soon. Here are some of our results on the number of uranium lines versus the number of thorium lines in the near-infrared. In the uranium here is shown at the top. You can see some issues with detector sensitivity. These uranium lines are derived from archived FTS data. So we expect that there are more uranium lines in this gap around 1.1 or 1.2 microns, but we weren't able to find them in our data. And the thorium is shown here as well from Kerber 2008. It's not exactly a fair comparison. The Kerber data was taken at a lower current, so we do expect that we know there are more thorium lines than are shown in this histogram, but for what's currently available, this is representative. And the number of argon and neon lines in this region is shown in the bottom plot as well. The wavelength scale is at the top. So when we went to the HET in April and May, we observed several M-type targets and some other radial velocity and planet hosting stars, some of which are shown here. This is GJ412. You can see the stellar spectrum, which is very bright compared to the uranium neon. This is GJ436, Barnard star, GL273, and Tau Bu, which has a high rotation, which broadens the lines, which you can see here, especially in the bottom orders. And you can see telluric features in that very bottom order, as Subrith pointed out. And GJ406, we took this spectrum without the calibration source so we wouldn't contaminate the stellar spectrum, but you can see there's a lot of stellar information here. This is the same spectrum, the same star rather, that I showed, that Pavlenko took with his, in the earlier plot that I showed. Here's an extracted Tau Bu spectrum highlighting some of the lines in that spectrum. And a telluric standard highlighting again the relative lack of telluric features in this region. This is a movie showing our cross-correlation, one of our cross-correlation techniques. The idea is to use a mask derived from the solar line list and move that mask, shown here in the top plot here, across a variety of velocities, and then at each velocity calculate the summation in that mask, and then in this bottom plot you can see the cross correlation as you move that mask across. I'll show that one more time. It's hard to see, but you can actually see the mask moving across here in the top plot at the same time. And then we fit that cross correlation with a polynomial or a Gaussian and measure the minimum, from which we can derive velocities, which you've already seen today. So again, emphasizing we're achieving between 10 and 25 meter, or 10 and 20 meter per second precision in the Y band. So in conclusion, fiber-fed high-resolution near-infrared spectrographs are a very promising way to measure precise radial velocities in the near-infrared around M dwarfs. We provided a new calibration source which will be available to the community, not only for this work, but Apogee will be taking advantage of the uranium line list. We have found that uranium offers a greater line density than thorium does in the near-infrared, and we emphasize that neon is a better fill gas than argon in the near-infrared. I should have mentioned earlier too that we don't use these fill gas lines for precision radial velocities. As Whaling pointed out in 2002, some of the fill gas lines will shift depending on the pressures in the lamps. In the near future, we'll be publishing the uranium line list and the atlas, which will be available to the community. And I'll be working at NIST on other calibration sources for the near-infrared. And the Pathfinder team will continue to make the next generation of Pathfinder. I hear we've secured funding for the next detector, which will be 4 times the size. Thank you very much.